In this video, we're going to be looking at how to handle when the displacement of an object occurs in more than one direction. You can imagine, let's say for example, that you started at this location here and you went in some random displacement like that, delta d1, and for the heck of it, let's just say that that was 5 meters. And then you changed directions and you went down here, and again, for the heck of it, we'll say that that's 3 meters. Our old way of handling this would be to have said delta d total is equal to delta d1 plus delta d2, and so we would have said, 5 plus 3 equals 8. But I think we can see that your total change in position, or your delta d total, that actually occurs here, I don't know what it is, but it's not 8. You can't simply add these two numbers and expect to get the third number when the directional change happens like that. Just in case for some reason you're not seeing that that's not 8, like imagine if that's 5 and that's 3, this distance is 8. This and this obviously are not the same amount. So what we need to do is we need to find a way to simplify this problem to solve for the total displacement of an object that's moved in two different directions, and not just like forwards and backwards, but actually creating a two-dimensional plane. The approach we're going to take is going to be to split the displacements of the object into perpendicular directions. Then we can add those directions separately. Then we can recombine to find a answer. This can be called the component method, and the reason you'd call it the component method is when that vector is split into those individual directions, then you can see that those are the components that make up that vector. So just to repeat the diagram from the first place, we called this delta d1, but what if instead we represented delta d1 by a east, if you will. I haven't really set a direction, but let's just call that east, and a north part. So we would call this delta d1 north, and this one delta d1 east. Alternatively then, just taking a quick look, I made my delta 2 look like this. And what we're essentially saying then is that we will take the components of this vector, and so we would call this delta d2 east and delta d2 south, and we're going to see how that turns into a negative when we actually get into the math of this. But what we're actually saying here is if you went up like this and then you came down like that to get this total displacement, this can be represented as if you went this way and then I wanted that in red so that all of my north and south stuff is in red. I'm just going to make that quick change. Delta d2 south. So we went delta d1 all the way up there, and then delta d2, that would be back down like that. So that corresponds to that. And then, so basically we treated it like you went north and south, and now we're going to deal with like when you went east. So then you went east some distance of delta d1, and then some other distance of delta d2, and those things overall will give you your total displacement. I'm not sure that diagram makes it as clear as possible, so let me just re-say that in a different way. So again, we're going to go up here, down here. That's the actual motion, but we're going to treat it instead like you went up, you went over, so we'll call that delta d1. So it's like you're walking around a square that represents the square that is that total displacement. And then for delta d2, you go like this, and then like this, delta d2, and delta d2, These are east, east, north, south. And what we can see is by squaring off the directions, we can deal with each direction separately. And then as a result, if we consider the totals, like this one here would be delta D total in the east direction, and it works out to a difference because they have different signs, but really what we're talking about here is delta D total in the north direction. We can see that when we recombine those two resultant components, is the language that they use, then we're going to get the overall motion of the object. I think this might be easier to understand by diving into an example. So on a city block, you're going to walk, I'll do all my norths in green, you're going to walk 5 blocks north, then you're going to walk 3 blocks east, then you're going to walk 2 more blocks north, then you're going to block how much? 5 blocks west. So your total displacement here is from where you started to where you're finished, like that. Okay? But it doesn't really matter what order you did these individual things in, and it's a little bit confusing here because if we went north and then east, this north obviously is going to be related to this north, and so the order that we've done these things in is not helping us see the overall situation. Instead, if I want to do north and east, then what I can recognize is that my delta D1, which was 5, and my delta D3, which was 2, both correspond to this direction. I'm going to use the unit blocks for B because I don't have a specific unit for distance here. What that means then is that my total distance in that direction is 5 blocks plus 2 blocks, or a total of 7 blocks. We can see this again. We always try to keep some sort of root and common sense here. You went 5 and 2, so the total that you went up was 7. Okay, alternatively in the east direction, we can say that delta D1, you would have come over a distance of 3 blocks, and then delta D, I guess that's delta D3, that's 2 and 4 actually, isn't it? 2 and 4. This is coming back, so this is 3, and this is coming back 5, but because it's going west, it's going to be a negative, so that's negative 5 blocks. The total displacement then is equal to negative 5 blocks. I'll do them in the order that they're given. 3 blocks plus a negative 5 blocks, or a negative 2 blocks. Again, thinking about that in common sense, you went 3 this way and negative 5 that way, so this little section right here is 2 blocks. So by separating out into the individual directions, we're able to add the vectors separately. Having added the vectors in each direction separately, we're able to get a north part of the movement, and in this particular case, a west part of the movement. What we now need to do if we want the overall part of the movement is we're going to have to solve that right angle triangle. We can use the Pythagorean theorem here. I'm just going to move over and redraw it so that I have space to work. So here I'm going to go over 2 and up 7. So if this is 2, this is 7, then I can use the Pythagorean theorem to find the length of the hypotenuse. H squared equals a squared plus b squared. And that works out to 7.3 meters. When you have a big component and a small component, the number almost always works out to be pretty close to the bigger of the two components. I also, again, I'm looking for a displacement, so I'm looking for a vector. So I've got to look at that angle there as well. Here I can use the fundamental trig ratio tan theta. That's going to be 7 over 2. So inverse tan of 7 over 2 is going to give me the actual angle. That works out to 74.1 degrees. Now, the way we specify this, we're going to say that the total displacement is equal to 7.3 meters east, 74.1 degrees. Actually, it's not east, is it? That's west. I often make mistakes with east and west, so pay attention to that as we're going through, and if you see them, let me know. Anyways, west 74.1 degrees towards the north direction. We always put the direction that we went in first into the heading. So there we go. We've used the components of a motion to come up with its overall displacement. I think this is a good place to pause, and we'll pick up when we're looking at a more complicated one.